I would like to spend further information on calibration itself. For this I made here my own calibration kit consisting of an open, short, match and through connection. And we'll now use this calibration kit on our VNA. So at first I will deactivate the offset correction we did before. And then let's check how an open really looks like. And we can see at very low frequencies, we start at the open point. And then as the frequency increases, we're circling around here with a slight attenuation while we are going more to the center of our Smith chart. And now let's just save this data as the trace data again. Let's call it 2. Now let's check the short connection. And this time we're starting here at the short point, circling around towards the center. Also saving this data here. As this is an educational video, I just made 2 calibration kits of it. You would use neither of them for a real measurement because they are not accurate enough compared to professional calibration kits. Never mind, the first version includes 200 ohms resistors soldered in parallel in order to obtain 50 ohms. And the second versions include a 20 decibels attenuator instead. So the idea is the incident wave gets attenuated by 20 decibels and then the reflected wave gets attenuated again by 20 decibels. The hope is to achieve a broadband 40 decibels attenuation. So let's just check out of curiosity which of those 2 versions work better. It's better than expected. We are here by minus 60 decibels up to 1 gigahertz. So this is really good. So all the energy gets transferred into heat. But then starting at 1 gigahertz, you can forget this calibration kit here. Now let's save this trace data here on trace, memory, data to new memory. So we have stored in the blue line now the actual data. And now let's compare it to the 20 decibels attenuator. So now first let's check the Smith chart. Blue are the 2 resistors and green is the attenuator. Now switch to the magnitude representation now, and as expected, our attenuator shows really a flat response of minus 40 decibels. But again, at 1 gigahertz, it gets worse. So in this case, the 2 resistors work better than the single attenuator. But let's just continue with the attenuator for now and kick out the previous trace and store the actual trace in another touchstone file. And now, just for educational purposes, I will create a new calibration kit in our VNA. In the calibration menu, go on Cal Devices, Calibration Kits, going to the SMA kits, and we'll just add a new one. We can go again to the standards and add here now an open with female gender, and we can either now set the values by our own, or we just import an S1P file, exactly the file we saved before. Adding the second trace, this time for the short, also a female connector, importing the S1P file, and the same for the match resistor, choosing a female connector and importing the S1P file. Just hit on the OK button, then I've renamed the kit into CoKit. And now let's start with a new calibration with open, short and match. And now we have to select an SMA kit with the CoKit gender male because our calibration kit is female. Let's start and overwrite with the open calibration. So, and let's finish with the final calibration. And now the key question is, where's our calibration plane? Is our calibration plane here, where the connector starts? Or is it here at the end of our trace? Let's check it. Plug in our open. And the answer is, it's exactly here, at the end or the start of our dielectricum. Here is our calibration plane. And what you can see on the Smith chart here is already the trace introduced by our SMA connector plus the trace of our open connector here. Again, this calibration kit is just for educational purposes. It can never compete with a professional one, so we just delete the kit before someone uses it by mistake. Here is the layout of our calibration kit in Altium Designer. And from the left to the right you can see here the open calibration, here the short connection, here the match, and the through connector. So there's nothing special on this PCB, and also on the back side there is no secret here. You might have recognized that the trace width is not arbitrarily chosen, but in our case we have here 2.2 millimeters in order to obtain a wave impedance of 50 ohms. So imagine you have your vector network analyzer connected here in a 50 ohm system, and we want to have it matched here. Otherwise we would provoke reflections here on the connection. And the question is, how do we know to choose the width of our trace in order to obtain 50 ohms? And as a quick reminder, so this is about the wave impedance. You can have a look here on the microstrip page on Wikipedia. So a microstrip is just the trace here on the top with a solid ground plane on the opposite side. And on this side you will find the formulas to calculate the wave impedance or the characteristic impedance. And the formulas originates from this paper here. And I've checked the formulas here, the new equations from 1975, and it looks like that the formulas published in this paper matches with the formulas here in Wikipedia. So I put those formulas here in MATLAB, and we can now perform here a calculation and sweeping the width of the trace. So you see that the wave impedance is a function of the width, but not just for the width, but also from the height. So this is this plot here. And now having those two plots, for explanation, you can take a look here on the transmission line theory, and you will find this formula here, which can be explained by taking a look on the capacitance value. Think about the distance between our trace and the ground plane. If we increase this distance, the height, then the capacitance value C has to decrease, resulting in an increase of our wave impedance. Exactly what you can see here in figure 3. The more distance, so the more height, the larger the wave impedance gets. And the same is for the trace width. So if you increase the width of our trace, would cause an increase of our capacitance value C, resulting in a decrease of our wave impedance, what you can see here in figure 1. So more width of the trace means less wave impedance. But now we don't have a microstrip line, but we have a coplanar waveguide. And on Wikipedia, unfortunately, there is no formula for calculating the wave impedance. So the difference now is here on the coplanar waveguide, we have a ground plane not just on the bottom of our trace, but also on the left and on the right side. The same that we have here on our PCB. And now there are different calculators online to calculate the wave impedance as we did in MATLAB. And one of these calculators is already implemented in Altium Designer. For this you need to go here on the Layer Stack Manager. And here you need to switch to the Impedance tab. And here on the right side, you need to activate the Properties panel, where we can select between different trace types. So you can just select the single microstrip, but you can also select the coplanar waveguide. And for the coplanar waveguide, we can now play around with the numbers. So instead of 2.2 millimeters, we can just say, let's take 3 millimeters. And this would result now in a decrease in wave impedance, as we've seen here on this plot. So if the width increases, the wave impedance decreases. So going back to 2.2 millimeters. And we can also play around with the height. So we can say, let's take just a 1 millimeter height for our PCB. Then also the wave impedance would decrease, as we have seen here in figure 3. So if we have less height, then the wave impedance decreases. So we need to play around with the numbers in order to get the 50 ohms impedance here. And the interesting thing is you will get different results depending on which calculator you're using. So a good approach is to check whether the calculated impedance is a good estimation before manufacturing. For this, we can use a simulation program like CSD. Now let's continue with two-port measurements. So first, we characterized our capacitor on the SMA connector performing a one-port calibration. This time we're doing a two-port calibration and two-port measurements using this PCB here. Again, this PCB is just made for educational purposes, for better understanding how it works by using this calibration kit. Because as you can see, our device under test, our capacitor, is placed exactly at 15 millimeters. Okay, now let's characterize the same capacitor in a two-port shunt-through configuration using the self-made calibration kit, and for this we need some cables. So let's check what an ideal kit means. If we go here to the SMA, we can check the open again. And for the stray capacitance, we see there is the value is 0, so there is no stray capacitance inside. And also the delay is selected with 0 seconds. The same is true for the short. Here we also have no delay, and also for the match there is no delay defined. And we can also check the through connector, and also here there is no delay. Again, we're going to the calibration tab, start the calibration, but this time we perform a two-port calibration with a through open short match calibration. We go next. And this time we select the ideal kit. So we are using the self-made calibration kit, but the calibration itself is done with the ideal kit. And this time we need to do the calibration for both ports. So for the two-port calibration, we also need this through calibration. And this time, S21 is equal to 0 decibels, or 1 in absolute values, meaning that all the energy that is applied at port 1 of our vector network analyzer is transmitted through port 2. Therefore, there are no reflections. Taking a look at S11 in our Smith chart, we can clearly see that the calibration with this self-made kit is nonsense, especially for the higher frequency regime. So let's change the stop frequency to 1 GHz. But still, one very interesting question remains. Where is now our calibration plane? Is it here, where the connector ends, or is it here, the end of our trace on our PCB? So just plug in our open connector here to answer this question. And we can see that most of our measuring points are now very close to the open point, meaning the calibration plane is now here at the end of our trace. But nonetheless, we can trust our results to the maximum of 1 GHz, more to 300 MHz. And because our calibration plane is now here, we can now skip the step with the port extension and can directly measure our device under test, because it is located directly where our calibration plane is located. And now let's check the results of our 100 nanofarad capacitor. Here we can take a look into S21 and we can activate again a marker to look for the minima here. And we see around 19.9 MHz we will find our resonance frequency. We can also plot again the Z parameters. And this time we can select shunt through impedance. Then changing the format to decibels on the y-axis and scaling the y-axis appropriately. And then we can see that we have at our resonance frequency an impedance of minus 35 dB ohms. That's quite a funny unit, isn't it? And now let me store again this trace for the next experiment by going here to trace config, going to the memory option and select data to new memory. So here we have the results of the one-part measurement, but now we did a two-part measurement. So let's check this file here. And we can see we have stored S21 this time, which means we also have to adapt the formula for calculation the impedance. So we are now taking this equation and have to select here the correct file, hit on the run button, and then we can see with our shunt through measurement, we have measured less inductance. So for a good RLC model, we now have to decrease our inductance. So let's decrease it to 0.5 nanohenry, which shows then a good agreement. And we can also decrease the ESR here a little bit. That's to 10 milliohms to get this curve here, which shows a really good agreement. I think this is a good point to discuss inductance here. To my understanding, we cannot say that this capacitor has 1 nanohenry and this capacitor has 0.5 nanohenry ESL, because inductance describes the phenomena that an alternating magnetic field induces a voltage, the electromotive force that opposes the change in current, and the magnetic field itself depends on the loop current. So depending on your measurement setup, you will achieve different values for your parasitic inductance.